Hello and good day, sir. My name is Jun from Section 1, Group 2, and these are my group mates. In this video, I will be presenting the validation method for our assignment 3 using Ansys. So this is our study case. The mass here representing the passenger coach, while the spring here represent the coupler. The first study case, the K1 is 550,000 Newton per meter, K2 is 350,000 Newton per meter, and the K3 is 150,000 Newton per meter. The difference between the first design and the second design are the K of the spring. As you can see, the K of the spring for the first design is different, as I mentioned just now. And the K for the spring in the second design is the same, which is 350,000 Newton per meter. The mass for both the design is the same. So before we start our validation method, we first need to do some assumption, which is this. We assume the material of the passenger coach is made of steel, and we assume the passenger coach is in square shape, which is the mass 1 and mass 2. And the density of the steel is 7,550 kg per meter cube. And by using this formula, we can get the volume of mass 1 and mass 2. By doing this calculation, mass per density, we can get that the volume of mass 1 is 0.133758 meter cube. And since we assume it is in square shape, we can get the dimension of mass 1 by doing this. And then we turn it into millimeter, we will get 511.415 millimeter. Then we do the same thing for mass 2. As you can see, the mass 2 is 1,400 kg. Then we do the same thing. Mass per density, we get the volume. Then we can get the dimension of mass 2, which is 562.885 millimeter. First of all, the first step is to open the workbench of the Ansys. Then we create a model. Then we create a geometry using the dimension we just calculated. First of all, go to the XY plane and then go to sketching. Oh, we want the facing here to the XY plane. Just draw a rectangular. Then we go to the dimension to set its dimension. We click semi-automatic. So this will be length 1, this will be length 2, this will be the vertical 3. Yep. So according to our calculation just now, if you still remember, for the mass 1, we are now drawing the mass 1, we have the length of this. So basically just key in the length of the mass 1. 511. Oh, it's in meter. So make sure you need to change the unit to millimeter. Oh, it's 511.415. The length 2, since it was a square as we just mentioned, so it will be the same. Just copy and paste. And for the vertical 3, it will actually be the length divided by 2. And we just zoom in. Yep, it is a square with the length of what we just calculated. After we're done setting the dimension, let's just extrude and apply the direction. Let's choose symmetry. And this one will be divided by 2. We want it extrude in the middle. And just click generate. Alright. Then we will draw another sketching of rectangular, maybe here. This is mass 2. Dimension, same thing, semi-automatic. Oh, and then we click horizontal. We need to define the distance between 2 of this mass, or you can call 2 of this passenger coach. And we need a dimension here. So same thing, let's define the length 4 first. As we just calculated, the length of the mass 2 will be 562.885. 562.885. The length 5 will be the same since it was a square, as we just discussed. The vertical 8 is here. Same as mass 1, it will be the length of it divided by 2. And we have the H7, the distance between two of the mass. We will just set it to 100 millimeter. Nice, let's just extrude it. Apply direction as symmetric. Same thing, divided by 2. We want to extrude in the middle. Generate, and yep, we have just done drawing our mass, our passenger coach. Next, let's proceed to the model. We wanted to edit the model. So now we have the model interface. First of all, we need to make sure the material is as intended. Structural steel, yes, which is what we assume. Correct. So let's proceed. Next, we start drawing the connection. Insert, we want spring, which is the coupler. So according to our first design, we have 3 different spring with different K. So now let's draw this. Let's draw the first spring with K of 550,000 Newton per meter. Since the unit is in Newton per millimeter, so it basically will be 550 Newton per millimeter. After setting up the stiffness of the spring, let's go to the scope. Since it will be here, the mass 1 to the ground, so we need to choose body to ground. The reference will be, first we need to select the scope. We choose here, apply. Just a simple explanation why we set the reference x coordinate to -100. This is because just now we draw the geometry. We clearly know that here, this line is the origin in the x-axis. So if we want the spring to go left in 100 millimeter of length, we need to set to -100 millimeter. Next, we will proceed to add another spring. So for the first design, the second spring will be 350,000 Newton per meter, which if we change to Newton per millimeter, it will be 350. So let's set the stiffness to 350. We want the scope to be body to body since it will be between two of the mass. And then for scope 1, we select here, apply. For scope 2, we select here and just click apply. And since the distance, just now we designed the geometry, we set it to 100, so the spring automatically, it will be 100 millimeter of the length. Lastly, let's insert the last spring at the right side of the mass 2. So according to our design, 150 Newton per millimeter for K3, 150. Next, it's body to ground, since mass 2 to the ground. For the scope, select here, applied. Aha. So why the spring go here? It's because we didn't set our reference x coordinate properly. So since we know that our origin is at here, you can see it come out from here, right? So basically we need to reset the reference x coordinate to here so that it could go at this direction. So how can we do it? Basically just the length of the mass A plus 100 millimeter plus the length of the mass B and plus 100 millimeter so that it could come out here at 100 millimeter of length. Now let's just do some simple calculations. So the length of mass A is plus 100 plus the length of mass B, which is 562.885, plus 100, which is the length of the spring we wanted it to come up from here. Just copy paste it to the reference x coordinate. Here we go. You can see the spring come out here at the length of 100 millimeter. So far we have done it. All the spring is added. Next we go to generate the mesh. After the mesh is being generated, we need to set the boundary condition by clicking this remote displacement. So we do it for the mesh one first. We click here, apply, and set all component to 0 except for x component. This is because this is a 2 degree of freedom system. There will be 2 mass times 1 axis. That's why it is 2 degree of system. So the system can only move in 1 axis. So we need to do the boundary condition. So only x-axis can move freely. So we done it for mass A, and we need to done it for mass 2. Apply, set all to 0 except for component x, so that our system can only move in x-axis. Alright. Lastly, we need to go to the analysis setting and set the max mode to find to 2, since it is a 2 degree of freedom system. So there will be 2 natural frequency. This is why we set this to 2. Lastly, we just solve it. So after it's done calculating, we can click solution and we can see the result we get. So for the first design, the lowest natural frequency for this system will be 2.3887 Hz. And still same for the first design, the highest natural frequency will be 5.0052 Hz. Now let's click both of it and create mode shade result. So this is the mode shape for the natural frequency of 2.3887 Hz for the first design, and let's see the animation. You can see when the mass 1 is moving at 0.40552, the mass 2 is moving at 0.76873, and they move at the same direction. So we basically can calculate the mode shape by using the max divided by the minimum, which is 0.76873 divided by so the mode shape for this one is, while the mass 1 is moving at 1, the mass 2 will be moving at 1.89. Now in this case, let's play the animation. This is the mode shape for the first design at the natural frequency of 5 Hz. And since it is moving at opposite direction, we can get a mode shape by doing the calculation of the minimum divided by the maximum. Now let's try it. 0.3511935. Okay. The maximum is 88765. And since both of the mass is moving at opposite direction, there will be a negative for this value. This basically means when the mass 1 moves 1 unit, the mass 2 will move the opposite direction at 0.396. So now for the first design, second natural frequency, which is 5 Hz, the second mode shade, when the mass 1 move at 1, the mass 2 move at opposite direction of negative 0.396, which makes sense, right? Now let's proceed to do the analysis for the second design. The only difference between the first design and the second design is the stiffness of the spring, which for the second design case, all the spring have the same stiffness, which is 350 Newton per millimeter. Now you can do it very quick by just edit the connections. For this one, 350, 350, 350, and then we just update the mesh, and then just solve it again. For the second design, the lowest frequency is 2.6768 Hz and the highest natural frequency is 4.7315. And now let's create mode shape. This is the mode shape for the second design and the lowest frequency of 2.6768 Hz. And you can see they are moving in the same direction. And obviously the mass 2 is moving more than the mass 1. Now let's calculate the mode shape by using the calculator. As you can see, the value here shows when the mass 1 moves at 0.59, the mass 2 moves at 0.68. So basically just use the maximum divided by the minimum. When the mass moves at 1, the mass 2 moves at 1.151. And next, let's go to this. This is the mode shape for the second design when the frequency is at its highest, which is 4.73. And you can see they are moving at the opposite direction. And to calculate the mode shape, let's use the minimum divided by the maximum. Since it is moving at opposite direction, so this value need to be negative. So basically it means that when the mass 1 is moving at 1, the mass 2 is moving at negative 0.651. Negative 0.651 for the second natural frequency of the second design. And now let's compare the result we get using the Ansys method and the result we get using the theoretical calculation method. And we can see the results are very, very similar. You may pause this video to see the similarity yourself. And that's all from me. Thank you.